At under 4 gigabytes, a 27 billion parameter model can run natively within the memory budget of an iPhone 17 Pro. Despite the reduction in bit depth, the 1-bit variant retains 90% of its full precision baseline performance across a 15 benchmark suite. Putting a massive frontier language model onto a mobile device requires forcing billions of parameters through extreme mathematical compression without breaking the underlying logic. A standard 27 billion parameter model in 16-bit precision occupies 54 gigabytes. Compressed to 4-bit, it still demands 18 gigabytes. This creates a bottleneck. A smartphone typically exposes just 6 gigabytes per app. The model, cache, and activations must fit strictly inside that limit. This memory gate is the absolute limiting factor for edge deployment, overriding raw processing speed as the primary hurdle. PrismML's Bonsai 27B is the first architecture of this capability class designed to pass through that exact boundary. The deployment of agentic AI is no longer a question of compute power, but a problem of memory capacity. The 1-bit Bonsai variant achieves a final operating footprint of 3.9 gigabytes, a size smaller than a full precision 2 billion parameter model. This enables local devices to execute multi-step reasoning, structured tool calls, and coherent agentic loops. The architecture also maintains a 262,000 token context window. Because it includes a compact vision tower, local workflows can parse screenshots and camera inputs without calling a remote server. Reducing 27 billion parameters to fit within a 4 gigabyte envelope requires an architecture that functions without the high-precision components typically found in compressed models. Raw intelligence and massive parameter scale are no longer strictly tethered to the storage limits of centralized data centers. Traditional quantization often relies on escape hatches, leaving complex layers in high precision to prevent the model's logic from collapsing. This animation maps the core rule of the Bonsai architecture: end-to-end low-bit representation with no high-precision exceptions. Compression spans the entire language network. The embeddings, attention mechanisms, and multi-layer perceptrons all operate under the same constraints. Even the language modeling head is fully compressed, eliminating the memory spike that often triggers out-of-memory errors on mobile. To handle multimodal tasks, a dedicated 4-bit vision tower snaps directly onto the main architecture. Bonsai counters the potential loss of information through a technique called group-wise scaling. By applying FP16 scaling to discrete groups of weights, the model brackets its values and preserves the critical outliers in the data distribution. Unlike hybrid approaches that mix precision levels and bloat the model's size, uniform compression is required to clear strict hardware boundaries. Leaving even a single major layer uncompressed would push the total footprint past the 6 gigabyte limit available on flagship mobile devices. The Bonsai 27B family provides a deliberate scale between output quality and physical footprint. On the left, the quality-oriented ternary variant restricts weights to a 3-state structure: -1, 0, and +1, yielding 1.71 effective bits per weight. This 5.9 gigabyte build is designed for laptop-class hardware, prioritizing maximum reasoning capability. On the right, the footprint-oriented 1-bit variant uses a binary structure of -1 and +1, dropping to 1.125 effective bits per weight. This 3.9 gigabyte structure specifically targets the tight memory budget of a smartphone. PrismML quantifies the efficiency of these trade-offs using a metric called intelligence density. The 1-bit variant achieves a density score of 0.53, measuring the amount of reasoning power packed into each gigabyte of storage. This is more than 10 times the density of the full precision baseline and 2.7 times higher than conventional low-bit alternatives. Model deployment is now a targeted engineering choice, optimized for the exact physics of the host device. This chart tracks performance across a 15 benchmark suite in maximum thinking mode. The ternary variant holds an overall score of 80.5, retaining 95% of full precision capability. The highly constrained 1-bit mobile build retains 90%, scoring 76.1. The data shows that while general knowledge benchmarks like MMLU see a 10-point drop, the model's performance in math and coding remains nearly untouched. Structured tool calling, the primary requirement for agentic work, stays within a few points of the full precision baseline. These low-bit configurations also unlock high throughput on consumer hardware, reaching up to 163 tokens per second on an RTX 5090. The retention of math and coding scores suggests that end-to-end quantization preserves core logical reasoning, even as the capacity for general information retrieval decreases. AI workloads are moving beyond single prompt responses into unattended, multi-step agentic workflows. This topology diagram contrasts centralized cloud execution with local edge nodes. For agentic loops, cloud execution imposes constraints, as costs accumulate with every remote request. Cloud-only agentic work also requires transmitting screenshots and private local documents across external networks. Local inference creates an economic inversion, where the marginal cost of a 100-step agentic loop is zero. This allows for a new category of persistent, offline digital assistants that reason over private local data by construction. Developers can now implement hybrid architectures where sensitive tasks remain local and only the hardest steps route to frontier cloud models. Embedding a model of this class directly into the hardware allows agentic AI to function as a persistent local utility rather than a metered service. Multimodal reasoning and reliable tool calling now fit on the devices users already own. PrismML has released these weights under an open-source Apache 2.0 license. Intelligence density, the amount of reasoning power packed into every gigabyte of storage, is the axis that will dictate the limits of AI deployment. As frontier inference capabilities relocate onto edge hardware, the economic dominance of centralized cloud models faces a structural challenge. High-tier intelligence is migrating from centralized server farms into the local silicon users carry in their pockets.